there are imperfections in the real world. That's why we couldn't achieve the theoretical strengths, for example. There could be a zero-dimensional imperfection, such as a self-interstitial error, or vacancy, empty site, interstitial, and the substitutional impurities. Impurities may occupy interstitial sites, for example, or it may replace the original host atoms. So those could be imperfections, as illustrated in this figure. You could see self-interstitial atom occupying the space it is not supposed to occupy. And you can see substitutional impurity atom, which acts as an imperfection in this case, and vacancy, empty site. This is supposed to be occupied by the host atom, but it's not there. And the interstitial impurity atom may be squeezed into the empty spot between the host atoms. One-dimensional imperfection is known as dislocation. And the dislocation is a very important concept you might want to keep in your mind. So A shows the edge dislocation. Basically, if you take a look, there's a missing lines of atoms. If you take a look at this figure from the side, the whole array of atoms is missing. And screw dislocation happens just like a screw is formed. Basically, when you start from the one end, and then when you just to make a random circle, it is supposed to come back to the original position, but due to the imperfection, then staircase-like shape is formed, and this mismatch is called screw dislocation. So there are two types of dislocations. One is edge dislocation in A, and another one is screw dislocation in B. The role of dislocation is important in the deformation. So take a look at this movement of edge dislocation. And then if you take a look at the figures from left to right, and then due to the presence of a dislocation, and then deformation is somehow facilitated. And this dotted line is a slip plane. And then due to this missing line of atoms, actually the movement of atoms is facilitated. So from left to the right, you can see to our eyes, it looks like this empty line is moving from left to right. So dislocation movement is often compared to the movement of an inchworm. It kind of bend and then move. So dislocation facilitates the movement of atoms due to this lacking array of atoms. So dislocation helps explain why the actual strength of metals is much lower than the predicted by theory. And the dislocation movement is also hampered by boundaries and then barriers. One good example is grain boundaries. So when grains are formed, while liquid metal, molten metal, is solidified, first a lot of nuclei are formed, and then these nuclei start growing, and then growing, and then finally they meet each other and then create grains. So within a single grain, we see well-aligned atoms, but we have multiple grains. The configuration and orientation of atoms are different from one grain to another. And then obviously we'll be able to see a lot of grain boundaries when we have a lot of grains. So in essence, these grain boundaries become the barrier for dislocation movement. So when we have a lot of grains, then we can expect a great degree of impediment by a lot of grain boundaries. So there is an empirical equation that describes the strength versus the size of grains. So we can expect higher strength when we have smaller grains, right? Because smaller grains result in a lot of grain boundaries, basically a lot of barriers for the dislocations movement. So this whole patch equation describes yield strength versus size of grain relationship. So sigma y, yield strength, is described by starting stress for dislocation, sigma 0, plus ky, this is a strengthening coefficient, divided by square root to d, and then d is the size of the grain.